Hello everyone, I'm Wan Chi from the National University of Singapore. I would like to share my work on online Markov decision processes with maximum fairness. So the model follows the conventional work, basically with a state space, action space, the initial state, the time horizon t, and the outcome distribution. So basically at every time t, the agent observes the current state, take an action, and receive an array of outcomes. So here, what's the difference is that we have k different types of rewards. So we denote t as v, and we allow the subsequent state st plus 1 and all the k types of rewards to be correlated in our model. And the action has to be chosen online in the model. So the objective is maximum fairness. So we start by defining the average type k rewards as the time average of the type k rewards collected in the t time steps. And the objective is to maximize the minimum reward, where the minimum is taken over the reward types. So in an uncertain model, the agent does not know the outcome distribution. In particular, she does not know the P, the transition probability, and the expected type K reward VK. And these important parameters are to be estimated online. So before we start, I would like to highlight important reachability assumption. Here, we first define the reachability by this random variable lambda. So it represents the number of time rounds needed to go from a state S to another S prime under stationary policy pi. So the communicating assumption says that for every 2 states, there exists a stationary policy, so that the number of time rounds to go from S to S prime under policy pi is finite, meaning that with a well-chosen policy, I can travel from one state to another in finite time. We see that this sort of communicating assumption is needed because if it is non-communicating, as the instance shown below, so if the agent is at S2, she cannot recover from her mistake and go to S1. So here it shows that reachability is essential. And concerning communicating MDP, an important notion is the diameter, which is basically the minimum time needed to travel between any two states. So a larger diameter means a more difficult problem instance. We quantify the convergence to optimality by the regret, which is the difference between our reward collected and the optimal benchmark defined as the optimal value of this optimization problem. The constraints are due to the classical work by Puterman, but we replace the reward by this max mean reward instead of a linear reward. Justifying the benchmark, we see that for any policy, the achieved reward is at most our benchmark plus a small error term. So our benchmark is asymptotically optimal. And our goal is to achieve a regret bound for which the regret shrinks with time, showing that the agent learns the model and converges to optimality. So our main contribution is the TMWU-UCRL2 algorithm, and we start with an overview. So basically the algorithm runs in episode. So the episode M starts at tau M and finishes at tau M plus 1 minus 1. And during an episode, I run a deterministic stationary policy denoted tilde pi M. So to fully describe the policy now, the algorithm now, I need to describe how we output tau M and tilde pi M. So tilde pi M can be computed by classical methods. So first we construct the confidence region for the latent parameters. Then we scalarize the reward by multiplicative weight update. And finally, we solve the scalarized latent problem, MDP, by extended VI, which is introduced by Jacks and authors. Our novel contribution is the determination of a tau m, which is by the novel gradient threshold procedure. So let me start with the confidence region. So the confidence regions are straightforward from the literature. Basically, we first define the count measure on how many times we visit a state action pair. And then we define the confidence region that is centered at the empirical mean of each reward type. And then the confidence radius defined based on the empirical Bernstein inequality. This is for V, and the confidence region for P is similar. And we can show that by the result by Audibert and others, the confidence regions contains the true parameters with high probability. And secondly is the scalarization by MWU. So first, consider a case when V is known. So in this case, I just take in a product with this scalarization, theta tau m at time tau m. And in the general time index theta t, the scalarization has this form, which is reminiscent of the classical MWU method. So the weight has a learning rate eta, which is equals to 1 over t to 2/3 here. It is smaller than the conventional choice here for technical reason. So we see that the weight theta tk increases when the reward collected in the previous time decreases. It means that if I collect too little of a reward k in previous time, my MWU scalarization will bump up the coefficient for reward k. It means, so this promotes maximum fairness. And then finally, when V is not known, we replace the latent V by the optimistically chosen V tilde M, where V tilde M is chosen from the confidence region. So this is the optimism in face of uncertainty principle. Finally, given the scalarized reward, we can solve for the tilde pi m by the extended VI. So to define what is the extended VI, we first define this notation for the optimal reward under scalar reward R and transition probability P. So basically, the extended VI will output tilde pi m, which is near optimal for the optimistically chosen P within the confidence region. So now we have described how we determine tilde pi m, but we see that only MWU and extended VIs are not sufficient. So this is witnessed in this example. So basically in this example, let's say we just naturally combine the two and we apply the two every time step. So what happens in this example? So in this example, every arc is a deterministic transition, and the factorial reward is denoted next to the arc. So in this example, what happens is that the agent would basically go to S1 loop one time, and then go to S2 loop one time, and then S1 loop one time, and so on. So it turns out that the collected reward for each type is 1/6, which is far away from the optimal value of 1/2 by the benchmark. So the issue here is that the agents switch among the stationary policies of looping S1 and looping S2 too often. In fact, she switches for T/3 times. So she wasted too much time at the center state. We reduce the switching by spacing out the tau m by using our novel gradient threshold procedure. Basically, the GTP serves as a pause button for the MWU, and at the start of tau m, it will decide when to start the next episode in the following procedure. So first, we initialize two measures, one distance measure and a count measure for each state action pair. At the end of each time step, I'll update the distance measure by adding the discrepancy between current scalarization and the initial scalarization in the episode. And I'll update my count metric in natural manner. And then I will announce a new episode when the distance measure is larger than 1, or when I visited a state action pair for enough number of times. So basically, the first criteria says that I move to a new episode when the current scalarization is so-called sufficiently different from the previous one. And the second one ensures estimation error bounded. It is basically by Jacks et al. In 2010. So let's see how the combination of GTP and the standard machinery solves the problem. So with GTP, it follows an interesting trajectory. So basically, if the agent is at S0 at time t, then if let's say she has less of reward 2, then she'll go to S2 and look for t to the 1/3 time, and then go back to the center. So vice versa. So basically, what we see is that as time progresses, the agent will spend longer time at each loop. So these reduce the switching and increase the time for collecting reward. So ultimately, we are able to get a regret of 1/2, 1/t to the 1/3. So the regret is strength with time t, which is different from our previous approach with 1/6. So let me conclude with our main result here. So our main result is that the previous observation generalized to any communicating instance. So we have this regret bound here. So the regret bound is for basically for a small state MDP. And we see that it does shrink with time. So let me conclude with some remarks. So first, the only no lower bound is by Jacks. And to close the bounds is an interesting question. And then we can also generalize from the mean objective to any concave objective, as done in the full version in 2019. And the work is also published in New Riffs in the last New Riffs. And then I also want to say that we can deal with the unknown t by the doubling trick. And finally, note that our algorithm is non-stationary, which is necessary in the sense that any stationary policy will incur a constant regret for infinitely many t. And then finally, for some unit chain instances, we can actually show that our algorithm converge in a faster rate than the optimal stationary policy. This is the end of my presentation. Thank you.